With that, we'll get into our next session. Thank you again to Johns Hopkins Applied Physics Laboratory and SAIC for your sponsorship. This session is Visionary Technology to Enable Science, and I'd like to welcome Peter Hughes, Chief Technologist at NASA Goddard Space Center. Thank you, Peter.
So good morning, everyone. I'm absolutely thrilled to be here to moderate this session that the AAS and the symposium committee put together for us. It's an eclectic array of capabilities and missions that have recently been developed or ongoing, but it is representative of the breadth of the type of technologies and new missions we are enabling within the space agency. I'll say we're almost at an inflection point, a unique inflection point in the area of technology and missions from various vantage points. First of all, there's a huge influx of VC capital flowing into our industry. As reported through Space Capital, somewhere around $17 billion the last quarter of 2021. We're also seeing a large number of capabilities throughout industry, not only the startups, but within the other government agencies, within our agency, NASA, and with our partners. And we're going to hear a collection of these today, of some of the things that have been represent some of the investments we've made over the past few decades, some of the stuff we've done recently, and some of the stuff we're making right now through Niki's program as we return to the moon. Another reason I think it's a unique inflection point is that there's a unique new role that I think the agency is taking on. We are not developing all these technologies. We are partnering a lot more with industry, with startups, with universities. And we have to depend on these new partnerships to enable these new type of visionary missions. And we're going to continue to do that over the coming decade. Since we last met in person, there's been some very exciting new developments. We've seen for OSIRIS-REx, the touch and go sample collection at Bennu. We've seen that the launch of Parker actually made it's the closest descent to the sun. We've witnessed, what were the other ones I had in my mind? Sorry, I thought I had this. Oh, and of course, the Ingenuity copter on another planetary surface on Mars. Very exciting missions, and I think even more exciting missions are on our doorstep. Today, of course, we're going to start with space logistics about a new servicing venture. It's a fully owned subsidiary under Northrop Grumman, but they are providing a new capability to service and improve the life of missions. And Niki's going to talk a bit about the game-changing program, or used to be the game-changing program, now the Technology Maturation Program, TMD, and all the wonders it's doing there to enable science on the surface of Moon, and also enabling next-generation capabilities throughout the agency and with all of our partners. Zibi's going to be talking a bit about a very, very exciting mission about the Dragonfly mission to Titan, and one of the Saturnian moons, and a very large copter to be able to rove using flight. And it's very, very exciting. So I can't wait to hear about this. And Dave, of course, is going to talk about the several platforms and ultra long duration balloons at WASP that's enabling next generation spaceflight. So with that, what I'd like to do is invite Jared, if you want to start first, giving each of the panelists approximately 10 minutes. I'll give you warning if you're going over. I will handle questions after the session. So get ready, because we're going to have a great session. Thank you. Jared?
Okay, thank you. First, it's a great honor to be here to talk about space logistics. I want to make sure that we got this, because I do believe I have the handy dandy clicker in my hand. There we go. So I'm Jared Rieckewald. I'm the Director of Government Business for Space Logistics. Dr. John Ehrenberg, who was on panel yesterday, working together. So today I'd like to go over briefly what we're doing in space logistics today, some of the accomplishments that we have shown in orbit at GEO with customers, including Mission Extension Vehicle 1 docking with Intelsat 901 in February 2020 at Graveyard, and then more importantly, Intelsat 1002 being serviced by Mission Extension Vehicle 2 in its orbital slot while broadcasting in April of 2022. And it's down by. Okay, so quick space logistics. We are a wholly owned subsidiary of Northrop Grumman. We're a Northrop Grumman venture. What you see here are actual pictures from space. So on the left-hand side, you see a picture of Intelsat 901. before MEV1 docked with it in February 2020. The bottom right-hand corner, what you see is from the docking camera of Intelsat 901, and that is our capture probe going through the liquid apogee engine of Intelsat 901. Roughly 85% all GEO satellites have a liquid apogee engine. It's how they got. It's how they got through GTO. So it's structural. It's near the center of mass. It is not used after the orbit raising. And so our mission extension vehicle, and we'll talk a little bit about mission extension pods coming up. That is how we mechanically dock with these assets that were unprepared for servicing and are able to extend their lives, augment their missions, improve their capabilities. And again, we have 2 on orbit generating revenues now. All right, here it is first. There we go. Quick fact sheet on the mission extension vehicle. So again, mechanical docking only. It does not communicate with the host. We coordinate mission operations center to mission operations center with the client vehicle. It's designed for 15 years of mission life, and it's designed to dock multiple times and have multiple clients. So mission extension vehicles 1 and 2 have 5-year leases with Intelsat 901 and 1002 respectively. But there's about 30 years of Delta V on the mission extension vehicles. And that's so they can do inclination pull downs. They can do relocations to Grayfield. They can do multiple missions, not just 15 years of life extension and attitude control for any one client or any multiple clients. Dual fault tolerant design, and it can be purchased, it can be leased. We have 2 operating in orbit today. What we see here is the 1002 docking from April. So this is the narrow field of view on the left of the visible and the IR on the right. If you go on YouTube, there's actually a 35-second video that condenses the last 11 hours of the 1002 docking, showing our circumnavigation of the client, how we move around from behind, below, come up on the R bar and move from our far hold to our near hold, and then actually conduct the docking. One other fun thing here is when we talked with 1002, again, it was in its operational slot broadcasting, 14 million paying customers, and there were some very important football/soccer games happening right now. And it was at prime time, so it was about 12:30 local. So there would have been very, very grumpy customers for Intelsat if something had gone wrong, but there was absolutely zero disruption of service. So why is that important? Obviously, whether it's NASA and the scientific missions or the Department of Defense and national security missions, no one wants to take their satellites out of mission to be serviced or to be improved. And through the near zero transient docking we demonstrated with Intelsat 1002 and Mission Extension Vehicle 2, we've shown we can do that. So it opens the door for military missions, for MilSatCom, for imagers, aperture sensors that can't be taken off mission to be extended or improved. And we're excited about where we want to go with this. So quick status of our assets. The bottom I'll pay attention to here because I've talked about the tops. Next thing coming down the pike is the Mission Robotics vehicle. What that is, it's an MEV with the DARPA RSGS platform. That is the robotic servicing of geosynchronous satellites. 2 large dexterous friend arms that opens the door for repair, for anomaly resolution, for assembly, and all sorts of other wonderful missions at GEO. We just completed a study for GO17 to look at mitigating the thermal challenge they have, the primary imager. And so that is a mission that could be something that, NOAA and NASA use the Mission Robotics vehicle to install a sunshade to mitigate that thermal challenge and restore it to all missions, all times of day, all modes, all thermal environments. And so we're excited about that. Additionally, we're looking at other types of scientific missions here I'll get to in a minute. Here's a picture of the Mission Robotics vehicle on the left. You can see those arms that come from DARPA and Navy Research Lab. In the middle is the Mission Extension Pod. So while the Mission Extension vehicle is based on a GeoStar 3 bus, it's about the size of my minivan over in the parking garage. The Mission Extension Pod is about the size of my dishwasher. So this is a sale. This is a one-time install, not necessarily meant to be multiple. About 6 years of mission augmentation and life extension for a 2,000 kilogram client. And we have one signed customer. So Optus from Australia is the first Mission Extension Pod customer. That was announced about 3 weeks ago. and we're excited. So that will happen in 2025. We're launching the mission robotics vehicle with DARPA in May of 2024. And on the right hand side is just an example. Current capabilities is a slick sheet. I think we talked about most of this. I'll get to this last slide and talk about what I think you care most about. So today, covered that. Next, robotic servicing at GEO. So I talked about, being at an inflection point. I would say we're actually at a tipping point, and the tipping points are due next Thursday, everybody. I've got to get back to work and finish mine. And that's something we're looking at for the science mission, being able to use that mission robotics vehicle to replace multiple payloads, have a persistent platform where the platform is a power strip / USB strip in space. And the payloads themselves, the sensors for Earth science missions, the sensors looking out to the cislunar space for space control or awareness, are things that don't have to last as long as the bus itself. Okay. And then, concurrent with that, we're looking at other missions that aren't necessarily with the MRV. So I mentioned Dr. John Ehrenberg, John Way for everybody. John is, in addition to all the great things he's done for us on a number of the great observatories, and certainly James Webb, we're also looking to service Chandra X-ray. She's in a HEO orbit, has some thermal challenges. Some actually made the news about 4 weeks ago. This would be a purpose-built servicer on the cheap, be able to extend Chandra for a couple. Okay. Sorry. Freaked you out with the whole Chandra thing. Snarf your coffee. You're a little scared. Okay, that's fine. This is good stuff. It would be a purpose-built servicer. We're on the cheap. We could extend Chandra by decades. Obviously, the links was not prioritized in this year's Decale survey. We believe that we can put a dedicated servicer up to rendezvous with Chandra in a non-destructive way, solve the thermal challenge, and extend her life. We also have plans, and we're actually spending resources on that right now. Our plan is to deliver an unsolicited proposal to NASA later this year to look at studying that in earnest, to be able to maintain the scientific relevance of Chandra going forward until such time as another major observatory in the X-ray family is prioritized. Understanding that's a resource issue and priorities issue. I used to be a Senate staffer. I am much better now, I think. So we understand how that game is played, but we think we have options that can help NASA sustain that mission at a fraction of the price of a new observatory of that family. Additionally, looking at Hubble, we've done some work on that. Certainly propulsion is an issue, but propulsion with scientific precision is really the challenge there. And there's still more work to do. The mission extension vehicle is precise enough at GEO for commercial geosatcoms and the swath of ground they cover for their customers. That is nowhere near precise enough for Hubble. I'm not trying to say it is, but we think we have some options there insofar as Hubble was actually designed to be serviceable by space shuttle, not necessarily by other robots. But we're putting together ideas on that and hope to have something worthy of discussion within the next 2 years for NASA and other partners in this realm, because Webb is not a replacement for Hubble. Hubble is still important, still scientifically relevant. We want to do what we can there, and we believe the technologies we've proven with mission extension vehicles 1 and 2, what we're proving right now with DARPA on mission robotics vehicle, can be used to great effect for the scientific community, sustaining the assets that we have, and then especially looking forward to designing things for serviceability. So we Space Logistics have a couple of refueling contracts with the Department of Defense. Can't speak about who specifically they are, but one's for a depot, one's for operational systems. So thinking about future spacecraft and buses, designing them for serviceability, designing them for refueling, designing them to be grappled, designing them to have things to be placed on them, power and data ports, fiducials. All of this is critical to unlocking the true potential of making these platforms more persistent, more resilient, and more cost-effective going forward. And I think that's my get off the stage.
All right, thank you. I forgot to do something. When I was going to introduce the panelists, I was not going to go through the VCs. Instead, I asked them for an interesting factoid on each one that none of you may know. The first one with Jared, he actually shared the fact that he, as a junior, as he was growing up, he was a junior golfer in the Southern California Golf League and got pummeled repeatedly incessantly. like Tiger Woods. Very different. We are gonna switch over to Dragonfly. We're gonna go to the order we had, and Zibi Turtle is the PI. I'm pleased to have her here. Her little factoid is that she's an active rower in the sport of rowing, and up in the rivers of Baltimore, I guess it's Pasco up there, where the Baltimore Rowing Club. So this is what she does to unwind when she's not preparing for this exciting new mission. Zibi?
Thanks. I'm really pleased to be here today to talk about Dragonfly and what we'll do. I'm going to
Press down to go forward.
okay. Thank you. So I'm going to really briefly talk about the mission, give an introduction to Titan, what we're going to do there, and then talk about how we're doing it. So Dragonfly is a New Frontiers mission to Saturn's moon Titan, selected in 2019. We're coming up on our preliminary design review this fall, so it's busy time. And gearing up for launch in 2027, which gets us out to Saturn and Titan by 2034. So Titan is a pretty unique place in our solar system. It's actually between Mercury and Mars in size, but in terms of its atmosphere, which is unusual for a satellite to begin with, its atmosphere is actually between Earth and Venus, which we heard a lot about this morning, in density. So the atmosphere at Titan is 4 times as dense as the atmosphere here in this room, or 1.5 times the surface pressure. So it's much more substantial atmosphere than we have here on Earth. See, I'm gonna get that. And the atmosphere is primarily nitrogen like our atmosphere, but it's got a second major constituent, methane, which makes things interesting in a number of ways. One of which is this photochemistry at the top of the atmosphere where the methane is broken down, recombines to form very complex carbon molecules. These molecules fall out of the atmosphere onto the surface of an icy satellite, where if you have melting of the water ice crust, now you have water and organic material mixing possibly for extended periods of time. So this is why Titan is such an important destination for understanding prebiotic chemistry and the processes that may have supported the development of life here on Earth. So we know Titan has the key ingredients necessary for life. It's got energy in the form of sunlight that drives this very rich photochemistry. It's got organic material that results from that photochemistry. And it has not one but 2 liquids in the system. There's water, which has been available at the surface of Titan's past at sites of impact cratering or possibly cryovolcanism, but also in its deep interior liquid water ocean today. And there's liquid methane, because methane in Titan's system plays the same role that water does here. And so you have methane clouds, and methane rain, lakes and rivers and seas, and it's possible that methane could act as a solvent for exotic prebiotic or even biological systems. So the science that we want to achieve with Dragonfly at Titan is chemistry. We want to understand the prebiotic chemistry, how far this has progressed in an environment that we know has all the ingredients for life, certainly life or has had it. We want to put that in the context of Titan's environment to understand its atmosphere, the organic transport, mixing of materials, the opportunities for those materials to mix with reservoirs. To understand the habitability of the Titan environment. And then we also have the capability to search for chemical biosignatures if chemistry actually took the lead to biology, not that we expect that on Titan, but we have the capability to identify those. So a few really quick facts about Titan. The surface gravity is about 1/7 the gravity here on Earth. I talked about the surface, the atmospheric pressure at the surface. The surface temperature is a balmy 94 Kelvin, so it's a very different environment in terms of the materials and the temperatures. But we actually have found that Titan's surface is surprisingly Earth-like. A lot of the same processes occur to form landforms on Titan with very different materials. So that's going to be very interesting to explore. And then deep beneath the water ice crust, there is a liquid water ocean, as I mentioned. So we know from the joint NASA-ESA Cassini-Huygens mission a lot about Titan and its atmosphere and its surface. We know there are a variety of materials on the surface, And so we know where we want to go to search for answers to really key questions about chemical origins of life. And so thanks to its atmosphere, Dragonfly can actually be designed as an octocopter, a rotorcraft that allows us to travel from place to place, the same way we use mobile exploration on Mars to carry everything with us and be able to see what's beyond the immediate horizon. But on Titan, because of the low gravity and the higher density atmosphere, we can actually fly from place to place. We, as you see here in the little video, we have our high gain antenna. We don't have the same infrastructure at Titan that we do at Mars. So we have to do direct communication from the surface of Titan. So there are a number of factors that are different in our exploration, but it's going to be a really exciting way to explore the surface of Titan. Great. So very briefly, Dragonfly, we have a spacecraft with a cruise stage that will take us to Titan. We have an entry vehicle that will protect the lander as we get down into the atmosphere, but then the mission is the lander itself. And we referred to the size of the lander. This is just to give a sense. We tend to think about drones as pretty small because we're used to playing with them in our backyards. This is a Mars rover sized drone, which kind of underscores how much easier it is physically to fly on Titan than it is here on Earth. Certainly on Mars with a thinner atmosphere. So that's me with the one of our prototype rotors, just to give a scale of the lander. We have a payload designed to study the chemistry of Titan and the environment, including a mass spectrometer that's being built by Goddard Space Flight Center, a sampling system, a suite of geophysical and meteorological sensors, cameras, and a gamma ray and neutron spectrometer being built by APL and Goddard as well. So the Dragonfly exploration strategy, we will actually explore Titan for about 3 years, and over that time, we'll be able to traverse 100, 180 kilometers, depending on where we land in the landing ellipse near Titan's equator, to explore the units associated with the impact crater you see there, which is an 80-kilometer diameter impact crater. It will melt at the target crust, and therefore there's the opportunity for liquid water, and organic materials to be mixed for extended periods of time. So I'll talk a bit about the technologies, but one of the really enabling things for the Dragonfly mission, I know this is technology now, is that we don't need to invent new technologies. What the innovation with Dragonfly is the combination and application of existing technologies to exploring a new environment on Titan, and to enable the key science that we want to key science measurements we want to make there. So Titan is 8 to 10 AU away from Earth. So all of our activities will need to be autonomous. We have ground in the loop for communication back and forth after activities, but the activities themselves, the flights will need to be autonomous. So we actually have a leapfrog strategy where for each new landing site, we actually will fly past our previously scouted landing site and then do image correlations, optical navigation, mapping the surface as we go, and then we'll come back to the previously scouted site. As I said, we don't have the same infrastructure on Titan, Mars, so we can't do imaging from orbit at super high resolution to do scouting. We need to do our scouting for ourselves. So the optical navigation of the scouting is one of the key aspects of the technology, and we can do simulations using of the optical navigation system using terrestrial analogs that are quite good for the Titan terrain. We also do hazard detection and avoidance for each of our landing sites using onboard LiDAR. In addition to the simulations that we're actually doing a lot of testing. Much of the testing is done with this roughly half-scale model here in Maryland, but we actually had the opportunity to take this out to the dunes in the desert Southwest last fall to demonstrate the navigation system, the autonomous takeoff, traverse, and other aspects of the navigation system over terrain that is very much like the terrain we have that we'll be exploring on Titan in the next decade. We also have a lot of testing in the Titan environment, and so some of the technology is simply demonstrating is to build the pressure chambers needed to be able to demonstrate that instrumentation. That again is leveraged from existing instrumentation, some of which is already on Mars, in the Titan environment. And so we have a small chamber here. This you'll see why I call it small in a second. This is a APL investment in the mission of a Titan pressure environment chamber that we've been using for a couple of years. And if you remember that picture on the left, that's the same picture that's on the left here. We have a new chamber that's going to be coming online. That will be large enough to have the entire lander in it. So that's going to be really excellent for testing the entire system. I want to talk really briefly about some other aspects of missions that we need to think about. In addition to the technology, we need to think about the teaming and how we broaden participation in the teaming. So one of the things that we've been able to do on Dragonfly is with NASA's selection of our science enhancement option is to put together a student and early career guest investigator program where each year we're able to bring in some students to work on the development of the mission investigations. And this will continue throughout the mission, and then during the science operations phase that will continue as well. But the projects are not only related to science, but also to the technology needed to achieve that science with our instrument packages. And then we also finally want to find ways to engage the community, of course, and we have the technology through augmented reality, virtual reality systems that we use for our design and build and operation of spacecraft, but those can also be very valuable tools for expanding participation here on Earth. And so we have the technologies that enable the mission to achieve the science, but we also want to find ways to use new technologies to expand the participation among everyone here, so everyone can share in the excitement of exploring Titan. So I will
That was exceptional. Thank you so much for that full mission overview and the use of technology and community engagement. Very, very fascinating. As you can understand, I would have loved to spend 40 minutes with each one of these presenters, but unfortunately they stayed within the bounds of our panel. The next speaker, Niki Werkheiser, is the director of the Technology Maturation Program. So let me get that right, Niki. Her little factoid is that she was a dual major. She also studied Slavic studies and spent a summer in Russia and a summer in Ukraine. And she's been in touch with her host family and actually hosted them here. Unfortunately, they're currently well, but they're all in our prayers. So with that, Niki, you're brilliant.
Yeah, good morning, everyone. Can you hear me okay? Yeah, okay. I can get loud. So 2 things I did learn is I have no athletic ability like the other 2 speakers here. And also you have really cool graphics. My graphics aren't that cool, but those are really good. So happy to be here this morning. As Peter mentioned, I'm in the Space Technology Mission Directorate. So I'm going to talk a little bit today about the work that we're doing there. I cannot do that, I don't think. Oops, okay. So what we like to say is technology drives exploration. And we really do strive to develop the transformative capabilities that we're going to need to enable new missions and new discoveries. So if you look across the top of the chart there, we really invest and ensure a broad range of capabilities, including space transportation, surface destinations, focus on sustainable living and working farther from Earth, and then transformative missions and discoveries. So the work we do, we really support a broad range of stakeholders and customers across the Science Mission Directorates and our human exploration as well as AR&D. And we do really span the whole technology readiness level spectrum. So as a matter of fact, our programs in the Directorate are aligned with the TRL spectrum. So we have our early stage innovation programs that of course focus more on lower TRL. So a lot of R&D, as well as we work with lots of grants, universities, small businesses, advanced concepts, and crowdsourcing challenges, which I'll talk a little bit about here too. And then we have our mid-TRL, which is technology maturation, which is admittedly biased. That's the area that I lead. And we're really kind of the bridge between that lower TRL R&D and that higher TRL mission and fusion engineering. So it's a lot of fun. People often call that the valley of death. I find it to be very exciting, getting over that hump and being able to develop kind of the prototypes and first gen of those new technologies. And then, of course, we have our high TRL technology demonstrations mission program, which is the kind of end goal is to get these technologies advanced enough that we can start infusing them into NASA and commercial missions, as well as terrestrial applications, of course. So today, I'm going to focus a good bit on the area that you see there in blue, even though I want to note that this says Lunar Surface Innovation Initiative, and that's where we'll be talking. Our LSI areas and all of these capabilities really have a lot of cross-cutting applications. So even if it's sometimes tagged as something that we're using on the moon, we're actually proving it out there, but it applies to a lot of different type of missions. And I'll talk about several cases of that. We're working with our Science Mission Directorate for science applications, including, for example, on Dragonfly, the LiDAR that was mentioned is one of the areas in our program that we're really excited about. So. Okay, so the Lunar Surface Innovation Initiative, the idea here, this was established just in 2019, and it's not a program, it's an initiative that works across all different programs and with different mission directorates and industries I'll talk about in academia. And the whole idea was just really to look and make sure that we have a good strategy to develop the technologies and transformative capabilities that we're going to need to operate on the surface. So number one, we had to really formulate and integrate across all these different technology maturation levels and come up with a good plan for that TRL pipeline. And then, of course, you're going to talk about this a lot. I'm very passionate about it. Really focus on leveraging innovative partnering and procurement approaches in order to expedite that technology development. I was talking to my mom recently saying, she's known my whole life I wanted to work for NASA. And she said, I just never thought I'd hear you get so excited about contracts and procurement and acquisition. And I said, you know what, Mom, I didn't either. But it's the truth, I am, because that's how we make things happen. And having the right partnering and leveraging our mutual strengths, I think, is really critical to this, seriously. Another thing I'll talk about is how important it is to utilize the early robotic lunar surface flight opportunity. So we work very closely with our science counterparts on the commercial lunar payload services opportunities to test out these technologies early. And then, of course, we established the Lunar Surface Innovation Consortium, which I'll talk about a little bit, that actually Johns Hopkins APL is the lead for, and we have our spring meeting come up here May 4th and 5th. So in terms of capability areas, like I mentioned, these are very kind of cross-cutting, but we do consider these to be, there's 6 here that we consider to be really kind of the fundamental areas for technology and capability development. In situ resource utilization, of course, we need to have the technologies for ISRU for collection, processing, storing, and use of in situ materials. Of course, we work with our science counterparts a good bit in reconnaissance and prospecting, and I'll talk some about a mission there that we're doing to help inform the Viper mission. And then, of course, to do ISRU or any of these type of things, we need surface power. We need power and energy storage, and really we look at kind of a broad range of technologies there for power generation, power management and distribution, and energy storage. And then these are all very interdisciplinary, because to do any of these things, you really have to be able to survive the extreme environments that you're in. We all know the lunar environment is quite harsh and extreme. And so to survive that lunar night, we really have to enable rovers and manipulators and other systems to be able to operate and survive in those conditions. And then, of course, to be able to get to the places you need to get to. Some of the most rich science, as well as some of the areas that we would want to get to, would be too dangerous for human interaction, like permanently shattered regions. So we're developing small rovers and scouts that can get to these locations. And then for excavation and construction, when we think about ISRU and then coupling that with manufacturing and assembly processes, then you can start to use those local resources to really build structures like landing pads or shelters, which is really important. And then dust mitigation. Dust mitigation is interesting because a lot of people not in this field or outside of this business, that might seem trivial at first blush. Of course, we learned from Apollo, it's really not. And that's why you hear it called dust mitigation and not dust solutions. We really do have to mitigate, and so we're working different capabilities through active, passive, and operational measures in order to do that. So I want to spend just a minute talking about some of our early, I'll say early to mid 2020 lunar surface demonstrations. Right now, across the whole portfolio, we have somewhere between 25 and 30 demonstrations planned. These are some of our earlier ones, and as I mentioned, we work closely with our science group there that leads the commercial lunar payload services. And these are so important, as I mentioned, because if we're going to develop this mid-TRL and really buy down the risk and really get these ready to infuse into missions, then we have to start now. We have to make those investments now. And what I like to say in space tech is what we try to do is really develop or buy down the fundamental technical risks, the primary technology hurdles, if you will, in any given capability at a relevant scale so that it can be scaled up and infused into those missions. So one of our early demos here is on CLIPS is PRIME, our polar resources ice mining experiment. It will have a mass spectrometer and a drill aboard called Trident, which are the same mass spec and drill that Viper will use. So this will help to inform in that mission as well. And then we have on that same mission, in addition to PRIME, we have our deployable hopper that was developed through an STMD tipping point with Intuitive Machines, as well as a 4G LTE communication demonstration that was also through a tipping point with Nokia and Intuitive Machines. Then we have on the next flight 19D, we have an electrodynamic dust shield, and we do a lot in the area, of course, of interdescent and landing, and work closely with industry there for an experiment called SCALPS, which is basically studying the lunar plume surface interactions. And then on CP11, I'm really excited about this little scout, or this little, you just call it a scout, it's too little called a river, it's a little baby river. The Cooperative Autonomous Distributed Robotic Explorers, thank God for acronyms, CADRE, as we call it, developed by JPL. The idea here is this is kind of an open source design for a small scout that can go different places. But the neat thing is you can carry different types of payloads about the size of a bar of soap, maybe a little bit larger than a bar of soap. And so we did a crowdsourcing challenge with this called Honey, I Shrunk the Payloads, and then Honey, I Shrunk the Payloads, the sequel. And we're in the process in early April of down selecting the finalists for that. I will get the opportunity to actually go to the moon on a cadre. And so we had a lot of fun working with the scientists there on the different types of little experiments and instrumentation that you could do using these little scouts. And then on CP12, we have the cold operable lunar deployable arm, or cold arm, which also includes our bulk metallic glass gears to help survive the lunar night. It's a real game changer that we'll be testing out. And just real quickly, I wanted to touch on kind of some of our demonstration strategy, and I'll use ISRU as an example for that. For ISRU, and this shows again how we have interdisciplinary connections between all of these different technology areas. So for ISRU, we really had kind of a leader-follower path, we call it, with ice mining and oxygen from regolith processes that will kind of work in a dual path. Again, working really closely with industry, academia, and as well as our NASA teams across different centers. So we have the PRIME mission that I already mentioned, be our first one. It will help inform SMG's Viper. It's going to be a very exciting mission. We add a rover to that. And then after that, we'll have 2 to 3 subsystem demonstrations of ISRU. These early missions, as well as our high fidelity ground demonstrations, will inform what processes we use for those 2 to 3 demos. And then that will all help to culminate in what we call the ISRU pilot plant for consumable production. So what I mentioned earlier about a given capability at a relevant scale, the pilot plant may be capable of producing possibly hundreds of kilograms, but would be scalable up to thousands. So again, we're very excited about that. And all of these things, you have to have power, you have to be able to use excavation, you have to survive the environment, so they all tie together. I want to spend just a moment talking about the Lunar Surface Innovation Consortium. And like you said in your presentation, it's so important that we are able to partner and work with the broader community to make this happen. So from day one, when LSI was established, it was important to us to have a consortium as part of this. And not just kind of your typical consortium, but a no-kidding way that we could interact on a regular basis with industry and academia, other government agencies and nonprofits. And so we did establish this, and as I mentioned, Johns Hopkins APL facilitates this. In addition to the biannual meetings that we have each year, and we have one coming up May 4th and 5th at APL, if everyone can attend. It'll be hybrid, so it'll be virtual and in-person options. We also have monthly virtual focus groups in each of the 6 capability areas that I mentioned. And so that gives us a chance to really interact on a monthly basis and have real technical discussions. And so we also have our other mission directorates involved, of course, and on the executive committee, our science mission directorate, as well as ESDMD for human exploration and others. And so everybody participates, and we actually have industry and academic partners that help to lead different subgroups in these technology areas, where we establish what the true gaps are for technology needs in order to meet the mission priorities. And so there's a lot of really good interaction there, and we publish the results. And so we've had those on a monthly basis, and then we have also thematic workshops quarterly. So for each of these groups, when we really see a theme that comes up that is really prevalent and is cross-cutting across these areas, we actually have this thematic workshop, which have been wildly successful and so much fun. One example is we just had one called Regolith to Rebar that was really cross-cutting between our ISRU, our excavation and construction. And so we have speakers that come from industry and academia that are on the supply side as well as the demand side. So they have kind of discussions, well, what do you really need? What are your requirements? What's your mission objectives? And then they can really think about how to develop and design and meet those needs. So it's been really excellent, and a lot of publications there on the APL site if you want to follow up. And then in terms of reach, we really engaged over 600 organizations across 50 states, and since 2019, you can see it right out there, and I'm going to finish up. Just want to mention real quick, you can register if you want for the Spring Consortium on the APL website. And then the tipping points, as you mentioned, and thank you for that, are due on the 31st, and we're very excited to get those.
Excellent, excellent, great overview, and it's really exciting, not only the technology, but the new methods they're going about to acquire and prototype this technology. So thank you, Niki, for the great presentation. And last but not least, my good friend Dave Pierce, Director Wallace. His factoid is he's what he called a recovering surfer, and he's just transitioned over into paddleboarding with his very active wife, and I've seen him in action down at the beach. So with that, Dave, it's all yours.
Thanks a lot, Peter. Nothing's more humorous to my wife than watching me paddleboard with her. And so, my dog is named Kobe. So I'm very proud of Kobe. It's my pleasure to be here with you today to tell you about NASA Goddard's Space Flight Center's Wallops Flight Facility. I'm joined by Bob Jamieson. Together, we are really excited about all the things that are going on at Goddard's largest remote facility. We're about 1,800 NASA civil servants and contractors. We're in the midst of really the next generation, the Artemis generation of exploration. But our career in our 77th year at Wallops has been about supporting the researcher. We're very proud of the support we provide to our science community. Just want to get this started. it's a really exciting time for us. As you know that we have capabilities, and I think much like what we've been talking about, we have special capabilities at WALLOPS. Our suborbital platforms that we manage for the Science Mission Directorate, our sounding rocket program, our scientific balloons, our airborne science aircraft, as well as our research range and our small satellites. But when you bring together our platforms with our people, our engineers and our project managers, along with our space tech investments in our facilities, then you start to see where, with our partnerships, it becomes distinctive in how we can support science. And that's what I really want to talk to you a little bit about. What's our niche? I mean, the core of suborbital has been about supporting scientists to turn ideas and nurture those technologies so that one day they'll be part of a flight project, a NASA science mission. We're very proud over the last 5 decades, we have turned over 6 dozen nascent technologies or instruments that are flying or have flown on orbiting spacecraft missions from NASA and the country that trace their heritage to suborbital flight. I'm very proud of just the recent support that we provided to Dr. Garvin in doing drop tests from a helicopter that supported early tests that supported Da Vinci proposal. That's how we're relevant. We love working, our suborbital team, collaboratively with our science community to support not just the development, but the integration tests, flight validation, ultimately leading to cutting edge science on suborbital. And I don't have to tell you that, you know, a Nobel Prize winning scientists have started out as graduate students working in suborbital, right? And it's just exciting to be a part of that. We offer our low cost, rapid tech maturation process. We have a skunkworks kind of way of doing things with our test facilities where our science teams can come in, work shoulder to shoulder with our folks and develop those instruments. We offer frequent flight opportunities with our suborbital platforms as well as our small satellites, including piggyback. So if you had a technology and you just need to get a quick flight on it, we'll work with you to get it flown along with the primary mission. Payloads are recovered, of course, they're refurbished and reflown. That's part of our value proposition. And it really makes for a great environment for early career scientists and engineers working together with PIs in a hands-on environment. It's really special to see it working. Here's a picture of recent teams at WALLOPS integrating their sounding rocket payloads prior to going to Alaska. Our engineering staff has a broad range of skills. We offer supporting tools for simulation as well as design lab functions. But our engineering team at WALLOPS is always looking to both mature and advance the capabilities of our platforms, but then also what kind of payload subsystems can we develop to facilitate science. Here's an example of that. Our sounding rocket team worked with JPL to do parachute testing for the design for the Perseverance rover. And we did 3 tests in the 17 to 18 timeframe. And as well as developing deployables, balloons, et cetera, that are going to aid in supporting the Mars sample return mission. Our scientific balloons, our next suborbital super pressure balloon test flight will occur in Wanaka in early May. The super pressure balloon, of course, is a closed hull balloon that can fly upwards of 100 days from any latitude. That combined with our suborbital, our second pointing system, it really creates a satellite on a string capability for telescopes to do astrophysics. So anyway, we're very excited about the suborbital capability of balloons to both do cutting edge science as well as mature other technologies. And again, this is a great platform for piggyback flights. Moving on to our small satellite capability and special orbital projects, We have facilities, clean room, test facilities to support researchers coming in and integrating their science instrument with a small satellite, a CubeSat. We supported Goddard's ESPA integration on Landsat 9 last year very successfully. We're currently building a ISS payload, a solar coronagraph that's going to go to the space station next year. And we're supporting STP with helping manage some of those CLIPS payloads that Niki talked about. So really exciting time in terms of this. And this is what really brings it all together. Our suborbital capability and that skunk works mentality combined with the advent, working with strategically with our commercial partners and the advent of commercial space at Wallops. Now we're going to have the ability to offer quick piggyback rides in a Saturn rocket kind of fashion with these small commercial launch vehicles. There you see Crystal Johnson with the head of the Space Agency from Australia, or excuse me, New Zealand. And of course, here's the ability to fly technologies in a relevant space environment, powering innovation, but also while reducing the risk of infusion of that technology in a future NASA science mission. And then, of course, you may have seen in the news that Rocket Lab announced about 10 days ago that they're bringing a Delta II class launch vehicle to Wallops called Neutron. They're going to have a brand new production facility. We're going to break ground on it. Dennis Andrusik, our center director, will be down there turning over the soil on April the 11th. And our first flight will be in 2024. So really excited about not just the primary payloads, but again, the ability to mature technologies by having piggyback ride along payloads. And looking at our launch rate from Wallops orbitally, you can see that there's a tipping point here around 2025. And we think that this is really with our suborbital experience and this burgeoning orbital capability, this is going to offer our researchers an opportunity to fly more technology more quickly. And with that, I'll end it. Thank you, Peter.
So first, let me ask for questions from the audience, but let me just lay the ground rules. I ask that you try to ask questions that are short, just 1 or 2 lines for the question and something that we can answer quickly. So with that, let me first poll the audience to see if there's any out there that they want to have. If not, I can use my moderator privileges and ask a few myself.
Hi, this is a question for Niki particularly. What are the primary outputs from the Moon ISRU that you see being useful as we move forward with Artemis and other missions for moon-based, permanent moon-based?
So yeah, we can talk about this for a long time, but I'll try to be fast, I promise. But honestly, I think it's game changing, right? If we're going to do this, and again, the moon is a test bed for Mars and other locations, and we have to be able to use consumables, not only for crew consumables, but for propulsion. And as I mentioned, for really excavation and construction and being able to build structures and live off the land, if you will. And I'll say that for us, it's really pivotal to work with industry in this area. We have a lot of NASA subject matter expertise, but we want to be purchasers, just like with 3D printing that we're doing in space. We want to buy the product, right? We want to be the anchor tenant, but we don't necessarily want to be the ones, we won't be the ones that own the technology and develop it. So we want to enable that to happen, and I think it'll really be transformative.
I have a question for Niki, if you don't. Niki, in everything you've shown and everything I've seen from STMD, there's no mention of lunar reconnaissance in the next generation in support of situational awareness for our women on the moon who will be living there in new environments. And LRO is 10 years old. We designed it in 2004. There's no follow-on for anything to bridge what we're doing, and for instance, in earth science with our friends across the river. None of that transferable. And I'm wondering, are we just going to forget that, or what are we going to do?
We are not forgetting that. I will say we work closely. So Space Tech develops the technologies for ISRU, but the reconnaissance, we work with our Science Mission Directorate to do that, and we are working with them on that. I think you wanted to add something.
I can put an NED on it.
Yeah. So Thank you for the softball question, because I agree, and that is something that we are working in through LSIC, we get that feedback from the community, and that does feedback to NASA.
For Zibi, I was wondering, right here. I was wondering, how long would it take to be able to communicate between Titan and Earth?
Right, so it varies depending on where Earth and Titan or Saturn, the Saturn system are in the orbits, but it's generally around 90 minutes. So yeah, there's a good amount of delay, which is why everything needs to be autonomous. Although we saw with Ingenuity, right? Ingenuity's flights are autonomous too, even though Mars is much closer. So fortunately, there's been a lot of work developing the capability for that kind of autonomous operation. So that you just have to be patient.
Dr. Turtle, also a question for you, Bonas NASA. I'm curious, that autonomous demonstration and use case is awesome. What about Titan's environment are you most worried about that you don't know for that autonomous?
We actually have characterized the environment pretty well. The Huygens probe, the ESA Huygens probe, descended, studied Titan's atmosphere, designed to descend down through the atmosphere, study the atmosphere, actually landed on the surface and images of the surface. And it turns out that with the new Frontiers program ending, Dragonfly will be arriving 1 Titan year after the Huygens probe descent. So so we know what the atmosphere was like at that time of year. We have a good characterization of the environment. The biggest challenge really is the thermal environment with the very cold temperatures.
Last question.
Me? Okay. This is also for Zibi. Regarding your Dragonfly, you're gonna be basically flying your drone over Titan to survey, map, inspect, different mountains and subsurfaces. I was wondering, you are still flying your drone over Titan, so what information are you hoping to get specifically from the subsurface ice layers, for example?
Yeah, so actually we spend most of our time stationary on the surface with flights about once a month, once every other Titan day. So we do actually spend most of our time on the surface. The geophysical package includes a seismometer and geophones. So we'll be able to listen for Titan quakes to find out how much seismic activity there is on an icy satellite with the interior water ocean. And so that would be very interesting depending on whether Titan cooperates with large Titan quakes. We may be able to understand more about the interior. We also have electric field sensors as part of that package, and so that we can look for the Schumann-Wilson sort of path systems.
Well, that's gonna be it. I want to have one final applause for our panelists and.
Yes, thank you very much to all the panelists. For all you locals, if you ever get the chance to go down to Wallops, please do. Just ring your doorbell, right? And then you'll take care of them. Yeah, absolutely. I went down there for a NASA social for the Labby launch, and it was just an amazing couple of days. Really neat facility. So thank you again very much to the panel. We appreciate it. We'll take a short break right now.